Hi, my name is Moksh S, and I'm a junior at Johns Creek High School. Today, I will be presenting PeptideAI, a machine learning model to help discover new antimicrobial peptides more efficiently. Firstly, antimicrobial peptides, or AMPs, are small proteins that can kill or stop the growth of bacteria. They're used to develop new treatments for diseases, but the problem is finding effective AMPs using traditional lab methods is slow, expensive, and labor-intensive. That's where AI comes in, to speed up this process. Instead of testing thousands of sequences in a lab, researchers can use my AI model to predict which peptides are most promising. This saves time, reduces costs, and addresses antimicrobial resistance, which is one of the biggest global health challenges today, killing millions per year. First, to train the model, I collected AMP and non-AMP sequences and then combined, cleaned, and filtered them, ensuring the model learned from high-quality data. To make our peptides machine readable, I used ProtBERT, a transformer model pre-trained on millions of protein sequences. ProtBERT converts each sequence into a vector to capture deep biochemical properties, giving our AI meaningful patterns to learn from. For the structure of the model, I built a fast multi-layer perceptron. Data flows from the input layer through two hidden layers where the core learning occurs. I used ReLU activation and dropout to maintain robustness. And finally, the sigmoid output provides the AMP probability. This simple structure allows for instant classification. To train the model, I used a standard 80-20 train test split with binary cross-entropy loss and the atom optimizer to find and correct any mistakes while learning. Our performance metrics display strong classification, with the confusion matrix showing the model identified most of the sequences correctly. To showcase my model, I built an interactive Streamlit app so anyone can use it. Firstly, users can use the main predict page where you can upload sequences and filter through a large amount of predictions. The Analyze page breaks down why the model made its decision. We highlight the 4 critical AMP properties and plot them against the ideal AMP range. The Optimize page uses an algorithm to mutate the sequence to boost the confidence score. The output shows the original versus the optimized sequence and how it got there. Finally, the Visualize page uses TSNE to make the model's complex understanding of peptides and compress it into a 2D plot. This can help researchers understand what characteristics are correlated with certain AMPs. This tool gives insight into why a sequence might be antimicrobial and how it can be improved. Overall, it supports faster, data-driven drug discovery and helps scientists focus on the most promising candidates to save lives. These are the technologies I used for this project. The core language is Python, and we use external libraries for data handling and model creation. I used Hugging Face for my transformer, and the front end was made with Streamlit. These are the sources I used for my presentation and the creation of my project. In conclusion, this project shows that AI can accelerate antimicrobial discovery. My app allows researchers to explore, predict, and optimize peptide sequences all in one place. The long-term goal is to find new treatments faster, helping in the fight against drug-resistant bacteria. Thank you so much for listening.